What is forward kinematics? Well, forward kinematics is the what happens if part of movement. In simple terms, we are given the joint angles, and we are trying to find the exact coordinates of where the hand or end effector will land in space. Think of it like a chain. You know the length of each arm segment, and you know exactly how much each joint is rotated. By adding up all those angles and segments using basic trigonometry and math, you can calculate the final XYZ position. Forward kinematics always starts with the variables you can directly change. For this robot arm, you control two things, and two things only, theta 1, which is the shoulder angle. You tell the shoulder motor, rotate exactly 45 degrees. This moves both L1 and leaders 2 together. And theta 2, the elbow angle. You want to tell the elbow motor to rotate exactly 30 degrees relative to where the upper arm is right now. This only moves L2. These two angles, theta 1 and theta 2, are the inputs to our forward kinematics function. Since there are two independent inputs, this system is defined as having 2 degrees of freedom to DOF.
Before we can find the hand, we must find the elbow. This is straightforward trigonometry. The shoulder is at 0, 0. The upper arm L1 is the hypotenuse of a right-angled triangle defined by the angle theta 1. The coordinates of the elbow, x1, y1, are x1 equals length 1 times by cosine theta 1, and y1 equals length 1 times by sine theta 1. Let's go through an example. In this case, we have L1 as 10 centimeters and theta 1 as 45 degrees. So if you look at the x1 formula, we can plug it straight in. That is, x1 equals 10 times by cosine 45 degrees, which equals to 7.07. Because we now got x, we want to find what is the y value for this joint 2 coordinate. To do that, we can just simply plug the same values into the y1 equation, which is y1 equals 10 times by sine 45 degrees, and you will get 7.07. So the final coordinate is x equals 7.07 and y equals 7.07. And remember that this coordinate is for joint 2, not the hand point or the very tip point. Now this is where beginners sometimes get confused. How is theta 2 measured? Well, look closely at the elbow joint in the diagram, the elbow angle. Theta 2 is measured relative to that dotted line. It is the angle the forearm L2 bends away from the straight line established by L1. To find the final horizontal and vertical components of L2, we need the angle of L2 relative to the ground, the x-axis. This angle is simply the sum of both joint rotations, which is theta 1 plus theta 2. We can calculate how much additional x and y distance L2 covers, starting from the elbow position. Change in x2 equals L2 times by cosine theta 1 plus theta 2. Change in y2 equals L2 times by sine theta 1 plus theta 2. The final position of the hand is the elbow position plus the L2. Displacement x final equals x1 plus change in x2 equals L1 times by cosine theta 1 plus L2 times by cosine theta 1 plus theta 2. Y final equals y1 plus change in y2 equals L1 times by sine theta 1 plus L2 times by sine theta 1 plus theta 2. Look back to the diagram. We got L2 as 7 centimeters and theta 2 as 30 degrees. We know x1 equals 7.07 and y1 equals 7.07. The total angle relative to the ground is 45 degrees plus 30 degrees equals 75 degrees. Now let's plug them into the new equation, which is x final equals 7.07 plus 7 times by cosine, 75 degrees, equals 7.07 plus 1.81. This equals 8.88. For y final, we do the same thing, which is 7.07 plus 7 times by sine 75 degrees, equals 7.07 plus 6.76 equals 13.83. And that's it. If you input 45 degrees, 30 degrees, the forward kinematics function tells us the hand lands at precisely 8.88, 13.83. Here's a practice task for you. Remember, the diagram is not drawn to scale. Can you calculate the final hand coordinate? The answers are on the right side of the screen. Now you might be asking, what happens if we add more joints? What if we have a 3 degree of freedom arm, a 5 degree of freedom arm, or an insanely complex snake robot with 100 degrees of freedom? Do we just keep adding the angles and arm lengths together? The short answer is yes. Conceptually, that is exactly what you do. If you add a third link, say link 3, its angle relative to the ground becomes theta 1 plus theta 2 plus theta 3. To find the new end effector, you would just add a third mathematical term to your equations using that combined angle. You are essentially just tracking a longer chain of connected triangles. It works great at a small size, but the real trouble starts when you try to expand. First, this simple angle addition trick only works if the robot is completely flat on a 2D plane, with all joints twisting in the exact same direction. The moment your robot moves into the 3D world, where the shoulder pitches up, the elbow swings sideways, and the wrist rotates, the math gets slightly difficult very quickly. You can no longer just add the angles together because they are rotating in entirely different dimensions. Second, manually writing out these equations for 5, 10, or 100 joints would result in massive, unreadable formulas. To solve this, advanced robotics doesn't use basic algebraic lines. Instead, we use matrix mathematics. We assign a special matrix to every single joint that describes its position and rotation relative to the joint before it. To find the end effector of a 100-joint robot, instead of adding 100 angles, we let a computer multiply 100 matrices together in a fraction of a millisecond. So while the concept of chaining remains exactly the same, the tool we use changes from basic high school trigonometry to linear algebra. And that's the end of this 2D forward kinematics tutorial. Hope this would help. Next lesson, we might step out of the flat 2D world and look at how forward kinematics solves the 3D space. See you there.